Okay, so in lesson 7.1, we kind of looked at all of some examples of nonlinear functions, and in this lesson, we're going to specifically dive a little bit deeper into exponential functions. And so the learning target for this lesson is I can model an exponential function in the form of y equals a times b to the x. And so we remember multiplication holds two letters together, so that just means multiplication. And so we're going to start off with a real life example and then extend it from there. So Julia has been hired by a company that will pay her $2 on the first day and will double her pay each day after the first. So thinking about this, we can start kind of filling out the table, and that will kind of help us look at what our numbers are. So it says complete the chart to determine how much Julia makes in dollars each day. And so the question you want to ask yourself is, would you take this job if they said, I'll pay you $2 on the first day and double your pay every day after the first? So after you fill out this table, you might have a better answer. So for day number 1, it says they'll pay her $2 on the first day, so 2. And then it will double her pay each day afterwards. So on the second day, she'll make $4. On the third day, she'll make $8. On the fourth day, she'll make $16, $32, $64, and then be careful, it kind of jumps up to 8 here. So I'm going to do 64 times 2, which is 128, and then times 2 again, that's 256. And then times 2, that will be 9 days, and times 2 will be 1,024. So by the 10th day, she's making $1,000 a day, which is pretty good. And I'm just going to not fill in this one. It's actually a really large number, so I'm going to kind of wait. But up to 10, that's how much she'll make. And it'll keep increasing after that. It'll double after that. So let's graph this real quick. So on the bottom, I think I'm going to do this. You'll see that this graph doesn't have any numbers on it, so we'll first label it. And so I think on the bottom, I am going to I'll go by ones all the way up to 10. I'll just skip 1. So this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll go up to 12. And x-axis is days in this case. Usually your x-axis is always your time. And then the pay, you'll see, is always an even number. So I'm going to count up, I think I'm going to do 4s for every 2. So I'm going to do 4, then 8, then 12, then 16, then 20, 24, 28, 32, 36, 40, 44, 48. And I won't be able to plot every single point, but I can at least plot most of them. So first I'll plot, I want to know what she makes at day 0. So if I go kind of backwards and say, all right, what's the initial pay before she even shows up? I would just kind of go backwards. So I'm multiplying by 2, I'm going to divide by 2, which is 1. So 0, 1 is my first point, which will be there, and then I'll plot 1, 2, then I'll plot 2, 4, then I'll plot 3, 8, and then 4, 16, and you can kind of see it's going up, 5, 32, 6, 64, but that will go off. So that's the most I can plot here, so I'll just kind of connect the dots. And I'll just continue it upwards and put an arrow to indicate that it goes on forever. So that's the relationship. And so when we talked about linear functions had constant rate of change, which means I could add the same thing every time, and that would make it a linear function. So let's look about how this function is increasing. This function is actually increasing by doubling. So to get from one y to the other, I'm actually multiplying by 2. So that's the pattern. Instead of adding or subtracting 2, exponential functions, you're multiplying or dividing. Okay, so it's increasing by multiplying by 2. And my y-intercept, we kind of found my y-intercept. That's where it crosses the y-axis, or where x is 0, and so that is 1. And so now that we have both of those pieces of information, we can actually write an exponential equation. So exponential functions can be modeled by the equation y equals a times b to the x, where a is the y-intercept and b is the rate of growth or decay. So my y-intercept here is 1, so I can put 1 in for a. And my rate of growth is multiplying by 2, and I can put 2 where b is. And so my equation for this could be modeled by 1 times 2 to the x. Or we could simplify this, because this is 1, to be 2 to the x power. So that is the equation for my exponential function. Both of these, either one. Okay, and so if I want to figure out what her pay would be on the 30th day, I would plug 30 in for x there, and then I could figure out what my output would be. So I would do 2 to the 30th, and that would tell me what my y value is. So that is exponential growth function. So let's look at another example about exponential decay. So this is called fighting fleas. After an animal receives a flea medicine, the medicine breaks down in the animal's bloodstream. With each hour, there is less medicine in the dog's bloodstream. The table and graph below show the amount of medicine in the dog's bloodstream for each hour for 6 hours after receiving a 400 milligram dose. So you can see the graph here, and then you see the table. So it's time, sense, dose, and then active medicine in the blood. So they're given 400 milligrams, and then it will decrease in the blood as time goes on, obviously. So this is a decay function. Okay, so it says, how does the medicine in the dog's blood change from 1 hour to the next? So if you look here, I'm increasing by 1 here. How is this changing? That's really what I'm interested in. So to get from 4 to 100, I would either divide by 4 or multiply by 0.25. So either one. Okay, and if I put it in my calculator, if I did 400 times 0.25, I would get 100, which is what I have in my table. And if I did 100 times 0.25, I would get 25, which is in my table. So I know that that's the rate that it's growing, or decaying in this case. So if you weren't sure about that, you can always take the second number and divide it by the first number. So I could take 100 divided by 400, and I know that I have to multiply it by 0.25 to get there. So my rate is I'm multiplying by 0.25 to get from one to the next. And you're really decreasing by 0.25 to get to the next, or dividing by 4. What is the initial amount given to the dog? The initial amount given to the dog is 400. That was our y-intercept. So it says, can you write an equation and model this using it in the form of y equals a times b to the x? So we need our y-intercept and our rate, which we have in a and b. So my equation will be 400, which was my y-intercept, times, and then my rate is 0.25 to the x power. And if you're not sure if that's right, you can always type that into y equals. And look at the table. Maybe not the graph. Well, the graph, but the table, and 0, when you get to 0, it should be the same as what's in the table that they gave you. So I know that that's correct because those numbers are the same. So this is what we call exponential decay. In a decay function, your rate will be between 0 and 1. It will always be a decimal, okay? In a growth function, it will be greater than 1. So if you look at our other one, this was greater than 1. So in a growth function, your factor will be greater than 1. In a decay function, you'll be less than 1. So let's look at a couple examples. So in the practice, you're really just practicing writing equations of an exponential relationship. So in 7.2, it's practice assess for each problem, identify its growth or decay function, and then write an equation to model. So if I look at this first one here, I can clearly tell that my y values are going down. So this is a decay function. So you first want to identify if it's growth or decay. And then in order to write my equation, I have to have my y-intercept. So my y-intercept is 2,000 in this case, because that's where x is 0. And now I want to find my rate. How is this decreasing? So to do that, I always take my second number and divide it by my first, just to see what I have to multiply by. So 1,500 divided by 2,000 is 0.75. So my rate is 0.75. It's decreasing by 0.75. And I could double check that. So my equation would be y equals 2,000 times 0.75 to the x power. Okay, and if you have a growth function, this number will be greater than 1. So that's all the practice is. On the other page, you'll see word problems, but it's the same thing. You want to find the y-intercept and the factor of growth or decay, and you're writing the same type of equation. In this graph, though, I want you to skip number 10. Just write number 9. And so for number 9, you might want to make a table of your x and y values, and that might help you write that equation.